So we are talking about the 555 timer, experiment 7, part D, and we are going to build the circuit uh, and take a look at the results or the square wave generated by that chip using Waveforms software and analog discovery board. We talked about the design equations, the internals of the circuit of the 555 timer, and how I can use resistors R1, R2, and C1 to control on time and off time and duty cycle and frequency, all of that. Now in experiment 7, the design is, if I keep scrolling down here, that. So let's zoom in there. So that's the circuit, figure D-5, that I am going to build. And I've already built that actually. So what I'm going to do is I'm going to relate the circuit diagram to the board. So my connections in detail and how they relate to the circuit diagram. So what is VCC? In my figure D5, I have VCC. That's essentially my plus 5 volt supply from analog discovery. That's the top rail here. The bottom rail is being used for ground, indicated by the black wire. Next, the simple connections first. That's always my process. So pin number 1 goes to ground. So that's the chip right in the middle, and you have a notch there on the left side. So that means that the leftmost pin on the bottom is pin number 1 through 4, 5 through 8. So if I look at pin number 1, that's connected to ground, and if I move this capacitor out of the way here, so pin number 1 is connected to ground using, okay, that's the best I can do in terms of zoom, using that black wire there. Then the next connection that we'll look at is pin number 4. Pin number 4 of the chip should be connected to the power rail, the plus 5 volts. So I have taken pin number 4 over here, which is the bottom rail rightmost pin. Using this purple wire, I have gone from this row to that row, another purple wire taking it from that location to that row, and then a red wire jumping it to plus 5, the power rail there. Next, pin number 8. Pin number 8 is the top row leftmost pin. Using that red wire, I have connected it to that power rail. Next is C2. C2 is capacitor of 0.01 microfarad value connected between pin number 5 and ground. So that is the capacitor 0.01 microfarad. The value on that should be 103, and it is. One end of that capacitor goes to pin number 5, which is the top row rightmost pin, and the other end goes to ground by connecting a jumper there and another jumper wire there to ground. Let's see. We have a resistor of value 1.8K between power rail and pin number 7. That resistor right there is power rail on one side, which is the 1.8K resistor. The color code is brown, gray, and red. The other end of that resistor is connected to pin number 7 there. And then the same pin 7 is connected to pin number 2 using a different resistor, 6.8K in this case. The color code is blue, gray, and red. Pin number 2 and pin number 6 are connected together because they are both monitoring the voltage of this capacitor C1 that appears in orange. That is the 0.01 microfarad capacitor that is connected between pin 2 and ground as shown. And pin 2 and pin 6 have been connected by taking pin 2 here, blue wire to jump to that location, blue wire jump to that location, green wire jump to pin 6. So that's how we have connected pin 2 and 6 together. What is left is pin 3. So pin 3 has a LED and a resistor in series connected to ground. So pin 3, long lead of the diode, red colored diode here, the short lead or the negative side of the red LED is on the other side, connected to ground using a 330 ohm resistor, which has a color code of orange, orange, brown. So that's your entire circuit. So I hope that you are able to map the circuit diagram to the each and every connection that I've shown you on this board. Okay, so let's zoom out a bit uh, and focus, and then start making the connections, and uh, let's see if it is able to generate the square wave. Uh, so I'm going to take the black wire, connect it to the analog discovery black wire, and take the red wire here, connect it to the red wire from analog discovery, and that's it. Those are the only two things that I need to connect. So what is fascinating to me, actually that's the first thing that fascinated me about this 555 timer, is that the input is constant, 5 volts, 9 volts, any voltage between 5 and 15 volts. It does not change with time. So the input to this is constant, DC voltage, but the output keeps going between low and high. It's a AC signal. So, the fact that we can generate that by using a capacitor charge and discharge cycle, that is what attracted me to this. Okay, so let's turn it on and let's see if it actually is going to generate a square wave. And because the LED is connected to the output of this chip, you would hope that the LED should blink. So let's see. I'm going to use waveforms here. I will go to the supplies tab, turn on the red wire plus 5, turn it on, and master is on. And as you can see, the LED is on. So the question is it on or is it blinking so fast that the human eye cannot see it? In the previous discussions about LEDs, I said, 30 hertz, 40 hertz, that's kind of the limit of the human eye. But, 100 hertz, for example, a human eye cannot uh, uh, distinguish between changes that happen at a speed of 100 times a second. So right now, the LED is blinking so fast that we cannot see it blinking. It appears on all the time. And I can make that comment, actually, I can validate that comment by actually measuring the output across that LED. So what I'll do is I'll use an orange wire to measure the voltage across LED, actually just the voltage output. So pin 3. So I've got an orange wire here. I can use that to connect to. Let's say I use orange to monitor the voltage across pin 2 and pin 6 because they are both connected together. I want to see how the capacitor charges and discharges. So I'm going to place channel 1 on that, and channel 2, which is the blue wire here, I'm going to connect that to the output of the timer, which is pin 3. So let's see. Come on. So I've connected that, and just so that I have less connections on the board, the blue stripe and the orange stripe have been connected to the black wire of analog discovery externally. So I've just connected it back to back using another wire that I am not showing over here. Okay, so what are we left with? We are left with turning things on, and we are going to turn on. The next question is that, well, do we have to turn on wave gen? Well, we don't have, actually, we don't need a wave gen in this case. Our 555 timer itself is the wave generator. So all we need to do is look at these voltages. One is voltage across the capacitor, and one is voltage across at the output of the timer chip. So we'll do that by using scope. So I'll use scope. I've already turned on the supplies, and I will run the scope. Actually, I don't need the I can make this the entire window, and I'm running the scope, and as you can see there is something happening. However, it's not in a good view. So what I can do is I can uh, probably make them 1 volt per division and 1 volt per division so that they are smaller, relatively smaller. I see a lot of noise. Let me turn off the noise on channel 1 followed by channel 2, and then I can bring them down a little bit, perhaps make the offset negative 2 volts on both channel 1 and channel 2 there. And these are too many time periods, so what I'll do is I will increase the plot width and reduce the time base to perhaps 500 microseconds per division. Question is, how did you turn off noise? If you look at this wheelie thing, wheelie symbol on the side of channel 1 and channel 2, there is an option for you to turn off thermal noise that is observed by the analog discovery. So I can turn it on and off. So I can do that for either channel. Okay. Okay. So that's it. The orange line, as you can see, shows charging and discharging of the capacitor. And as you might imagine, the time for which the blue one is on is dictated by the on time. We have derived the relations for that. So the time for which it is off is derived based on the off time equation, which is related to R1 and R2 and C. Oh, actually, the off time just depends on R2 and C1. On time depends on R1 and R2 and C1. Clearly, the duty cycle for this particular square wave looks like it is slightly above 50% because it is more on than off in one time period. But those are your voltages. Let me actually make this 500 so that it is a bit better in terms of the view. And we said the capacitor voltage toggles or goes back and forth between 1/3 VCC and 2/3 VCC. 1/3 VCC would be 5 divided by 3. So 5 divided by 3, 1.67 over here, and 3.333, which is 2/3 of 5 over here. So it goes back and forth over there. While the output goes between 0 and 3.6 something. So low, high, low, high, low, high, generating a square wave. However, based on the R1 and R2 and C1 values that are used, we are not really able to enjoy the LED blinking. So in order to slow things down, we are going to have to play with the component values. So we get a time period, perhaps close to 1 second. So if you look at your experiment 7 write-up, let's see, zoom out. Yeah, experiment 7 write-up says, to slow things down, use the same values of R1 and R2. However, you need to find a new value of C1 such that the time period is around 1 second. And then we'll replace our capacitor with this new capacitor. So because we will have a bigger capacitor now, so that it takes longer to charge up and charge down. So it takes longer to reach 2/3 VCC and discharge to 1/3 VCC, thereby making the time period slower. Actually, time period longer, 1 second. Frequency becomes slower. So let's try to do that. So for this, I'm going to turn off my supplies, and the moment I turn off the supplies, the scope goes to 0, 0 for everything. That's fine. I'm going to minimize well, I can just work on the circuit now. What I can do is I can pull out this capacitor that I don't need. However, I need to figure out what is the new capacitor value that I need to use. So what I'm going to do is I'm going to do some calculations that I will show you over here. So let's see. I hope that is visible. I need time period of 1 second. So t, which is essentially t1 plus t2, I need that to be about 1 second. So if I need that to be about 1 second, then I still need to use the same R1 and R2 values. So T1 earlier was derived 0.693, R1, R2, and C1. R1 is 1.8K, R2 in the design is 6.8K, and I need to find C1. And T2 is 0.693. Okay, this needs to be zoomed out. So T2 is 0.693, R2, C1, where R2 is that guy right there, 6.8K, C1 is unknown, but T, which is T1 plus T2, which is equal to 0.693 times R1 plus 2R2 times C1 should equal to 1 second, or just 1, as might confuse you. So 1. Which means given the value of R1 and R2, I should be able to calculate the value of C1 based on this equation. And it turns out that this value, if you do the calculation, should be about 137 microfarad capacitor. So I need to make this 137 microfarad capacitor so that I can get 1 second. And 1 second, of course, I'll be able to see the light blink. How do I get this? Well, in my parts, I had 100 microfarad. In my parts, I had 22 microfarad. I also had 47 microfarad. So what I did was I used 100 microfarad capacitor in parallel with 47 microfarad capacitor to get close to 137 microfarad capacitor. So that's what I did to, so I'm choosing, I guess what I'm trying to say is instead of 137, I used a 147 microfarad capacitor. Now, clearly, you might say, well, can you get closer than this? Well, of course, you can get closer than this. I could have used more capacitors. So I could have gone 100 plus 22 plus 10 plus 4.7. So I could have gotten very, very close to it, but I did not want to make it more complicated than it needs to be. So I'm using two capacitors to get pretty close, not exactly 1 second, but very close. But those are my design equations that you should take into account. So 147 microfarad, that's what we are going to put in our circuit. So let's see, having said that, let me pull this out. Let me bring back my circuit. And I've already removed my old capacitor, 0.1 microfarad. Now what I'm going to do is I'm going to place the bigger capacitor, 100 microfarad, between some point and ground, and I will also place my 47 microfarad capacitor from the same point to ground. So effectively they are now in parallel, and I will use a different wire, say a white wire, between pin number 2 to that same common point for the capacitors. So by making those connections, I have now connected pin number 2 to two capacitors that are in parallel and both go to ground. So let me zoom it so that you can get a good view. My voltages that I'm monitoring are still the output on the LED and the voltage on pin 2 or 6. That's the voltage on both capacitors. So now if I turn things on, hopefully you should be able to see the LED blink. So let's see, turn things on, and the LED is blinking very slowly. The total time for which it is on and off, if you sum that up, it should be slightly more than 1 second, because we have used a bigger capacitor compared to 137 microfarad. And the scope actually is going nowhere. The reason being, this is happening very slow. but the time base is of the order of 500 microseconds. So I need this to be 500 milliseconds. That will show me what this is doing exactly. So if I do a single acquisition, it should show me the complete wave. So still capacitor gets charged and discharged to the same 1/3 and 2/3 of 5 volts, but now the times have increased. The on time plus off time has increased to about 1 second. So that's the part of the experiment that we have done next. And now that we are seeing this LED blink, perhaps we can observe the timing signal by hearing something. So as a special treat, what I have for you is, I will leave this to be blinking. I will take a look at it later. I'm going to uh, show you a slightly different circuit. Same circuit, but different inputs and outputs. All right, let's see here. Um, so this might be slightly difficult to see. I'm intentionally making the room dark because what I have over here, I don't know if you guys are able to see this very clearly. Let's see, perhaps this should do it. So what I have is a Schmidt trigger in the not a Schmidt trigger, sorry, a 555 timer right in the middle. But I have replaced my R1 and R2 from being fixed resistors to photoresistors. So these are resistors that change the value of their resistance based on the amount of light in their surrounding. So that's my R1 and R2. So of course, if I change the lighting conditions, if I place my hand over it and I remove my hand, the photoresistors are going to go up and down. And when I do that, I'm going to be generating a different frequency square wave, which now I'm going to try to hear using a buzzer that is shown over here. So compared to the previous circuits, just a few differences. R1 and R2 now are variable light dependent resistors, LDRs or photoresistors. Earlier we had fixed resistors, and we have changed the output from LED to a buzzer. So let's see. I'm going to try to make the thing dark again so that you can hear things. And before we do this, I recommend that you lower your volume. It can get a bit uncomfortable on your ears. So try to lower the volume, and then we'll see how this works. All right, I hope you guys are ready. So I'm using a 9-volt battery instead of using the I'm using a 9-volt battery instead of using 5 volts from the analog discovery. The buzzer is buzzing at a particular frequency, and as I move anything really, so that's because I'm generating a different frequency tone that is detected by your ear, and you can sense the changes in those frequencies. Okay, so that's that's a quick demonstration of this special circuit that I had in mind. Let's put that by the side and let's come back to business. The last thing that you have, I would recommend now that you increase the volume. No more uncomfortable noise. Let's see, zoom out a bit. Now if I look at the experiment 7 write-up, the last thing that we have on there is, remember the counter, the 4-bit counter circuit that we had built in the last class, the one that you see on your right. We are going to use the 555 output, which is a square wave, to trigger our counter. Earlier we were using a wave generator from analog discovery to trigger our 4-bit counter. Now because we have the ability to generate a square wave, we can use this guy to trigger that guy. So what we'll do is, I'll still use the 1 second time period, and I will remove the LED that is blinking still at 1 second. I'll remove that. I will use a wire that takes it from the timer to the input of the counter. So it is going to pin number 1 of an inverter. It gets inverted and then that feeds into the clock input of the counter, which is the middle chip over here. But this guy is not going to go until I give it power and ground. So I'm going to take a copy of the power from the board on the left, and also I'm going to connect ground. So let's see, ground needs to be connected as well. So a copy of ground is given, a copy of this guy is given as well. Hold on, what? Yeah, that was a bad idea. Oh yeah, that my supplies are off. Okay, so my counter is now counting, and let's zoom in to take a quick. Alright, so I'm using the chip on the left here, well, the circuit on the left, which is a 555 timer that generates a square wave of time period 1 second, now as the triggering clock for the counter chip. Still we are inverting the clock first and then using that to get the clock input of the 4-bit counter. So it's still doing the counting, but now it's being triggered by a device that we made instead of analog waveforms, the analog discovery waveform. Okay, so that's the complete discussion on 555 timer, how a complete discussion on experiment 7 part D. Let me stop the recording and we'll take questions.